6.2 is going to be a continuation of rational functions and vertical asymptotes. The things that were in addition to yesterday is a function is increasing if it's a section of the graph that is going uphill from left to right. So what I think is, let's just take our parabola for just a minute. My little math bug, if he is walking downhill on the graph, then that section of the graph is decreasing. But if my little math bug, he only can look to the right, or we get to squish him, so he's only going to look to the right. And if he is looking to the right or walking to the right, and if he is going uphill on that section of the graph, that section of the graph is considered increasing. So an increasing or decreasing function is the height is increasing. The height is increasing from left to right. The height is decreasing from left to right. So that's what that terminology is talking about. So let's think about all the things that we are using as far as terminology when we look at the graph. When these x's happen, what is the function doing? So we have increasing, decreasing, we have positive and negative, we have zeros, we have going to infinity. So there's lots of language, but that's two little pieces I wanted you to know. Okay. This we talked about yesterday. So this notation, I just wanted to remind you one more time that if it has a little plus next to the number as a superscript there, if it has a little plus, we are approaching that a value from the right. If it has a little minus, we are approaching that value from the left side. That's going to come up when we do vertical asymptotes. We had talked about it yesterday. So this we talked about yesterday. This we've kind of mentioned a little bit here and there, but I did want to formally kind of tell you those definitions as we go through this. Okay. So that is just a few more terms that we've got. Again, I mentioned yesterday, one of the biggest part of this course is, what is the terminology referring to? It's a new language. So please make sure you're studying those terms. Okay. So if we look at our first example here, it says from each list, X is approaching notation to describe what value we are approaching, and are we coming in from the left or are we coming in from the right? So if we look at this list, it starts at 6 and then goes to 5 and then goes to 4.5 and then 4.55. Well, those two should have been switched. Sorry, I did type this out myself. 4.5001, 4.50001. What number are we getting closer and closer to? What number does it appear that we are getting closer and closer to? So we started out at 6, then we went to 5, then we're at 4.5, 5, and then we're at 4.5, and then we're at 4.5001, and then we're at 4.5.000001. What number are we approaching? 4.5. So the notation that would mean, and are we a little bit more than 4.5, or are we a little bit less than 4.5? More, right? That 0.0001 is more than 4.5. You got a little bit more. You don't got a lot more, but you got a little bit more. So how do you write that notation? Well, X is approaching 4.5. That's the first thing to figure out. What number are we approaching? 4.5. And since we're a little touch more than 4.5, I mean, definitely 6 was more than 4.5. 5 is more than 4.5. So we put the little notation, a little plus there, meaning we are coming in from the right side. The right side on our number line is a little bit more than the left side. Now let's take a look at B. Started at 9, then we went to 9.99, then 9.999, then 9.9999. What number are we heading toward? We're heading to 10. Is our numbers listed there more than 10 or less than 10? Less. So we put the little negative. Now, negative numbers can be deceiving. Let's think about the number negative 10. If it was negative 10 degrees outside, that is less than negative 2. So be careful, as the more negative we get, the less we are. So the notation for negatives can be a little funky, but let's just for a moment. First, let's see, what number are we approaching? Negative 5. Okay. So negative 4 is to the right of negative 5. So negative 5.001 actually is to the left of it. So that would be a little negative. So just be careful. Think about where it would appear on the number line. And I would even go with the highest one. 6 is to the right of 4.5. 9 is to the left of 10. Negative 6 is to the left of negative 5. That can help you. So that is just notation that's going to help us as we get closer and closer to an asymptote. That notation will appear. Yes. Yeah, that's what I changed. See. Oh, gosh, you're so right. Let's make this 4.5, 4.53. Thank you. I appreciate that. Yeah, when I was typing it out, I was putting zeros and okay, thank you. Yeah, or 4.51, 4.5. Okay, 0, 1, yeah, okay. Okay, let's take a look at number 2. Now, these are the function values. So these are the f of x's or the y values. And we want to know, does that appear if we were moving from left to right, if we had the x values that went with it, and we're going from left to right, so let's assume we're going from left to right, is the function going up or is the function going down? Well, for fractions, I think decimal values are very helpful, because when you look at a fraction and you're trying to compare it with another fraction, you either have to do the work of getting them common denominators, which is sometimes sucky, or you could just get them in their decimal values. Now, I'm going to go both methods for you. This is 8/16. This is 4/16. This is 2/16. And this is 1/16. So as you can see, how many 16ths we have is decreasing. So this is a decreasing section of a graph or of a function. Now, if we look at their decimal values, 0.5, 0.25, 0.125, and I never remember what a 16th is. 0.0625. If we think about which is the largest, in our tenths place, our largest value is 0.5. And then it goes in perfect decreasing order. So however you slice it, if you're comparing fractions, you either have to get them to be their decimal equivalent or a common denominator. Since all of these went into 16, that wasn't horrible to do. You decide. Same thing for B. Now, B is, again, deceiving. Negatives can be funky, okay? So this is negative 8/16, negative 4/16, negative 2/16, negative 1/16. Think about which one is closest to 0 and which one is furthest away. This one is also, or I'm sorry, it's getting closer to 0. It was further away. So this one is actually increasing. If we look at them on the number line, here is negative 0.5. Let's put 0 on there. Here is negative 0.25. Here is negative 1.25. And here is How about negative 0.125? And this one is negative 0.0625. So remember, our number line is naturally designed to go from least to greatest. So these numbers are getting bigger. These numbers are increasing or getting larger. And so be careful when it comes to negative values. They're a little deceiving. And sometimes I'll just kind of picture them on the number line to kind of decide what's really happening. So this is actually an increasing section of the graph. Those numbers are getting higher. So that's just a little thing I think that might come up in IMath. I think we're going to try to do that a little pre-class today together. We'll try. Okay. So now we're going to go back to our graphs for just a minute. And we're going to go back to our graphs that are related to our parent function. So it says to find the zeros, the y-intercept, the domain, the vertical asymptote, horizontal asymptote, explain what happens at both vertical and horizontal asymptotes. We have these functions to graph. Before we do any of that, I just want to remind you that our parent function, the reciprocal function, 1 over x, has a vertical asymptote at 0, 0 is undefined, has a horizontal asymptote at 0. Remember, if the x in our denominator has the higher power, it's always going to head to 0 on the ends. There's a swoop here and a swoop here. Okay, so always keep that in mind. So let's first analyze function A. I hope that you look at that and immediately go, that is my original function, moved to the right 8 units. So if it is a perfect relationship back to the original parent function, we know everything we need to know to graph that function. But I want to go through the process of finding all of the things that are listed up there so that we can then kind of put everything all together. Okay, so the zeros. The zeros of a rational function are where the fraction equals 0. A fraction will only equal 0 when the top equals 0. Does this fraction ever equal 0? Does it ever touch 0? Does our reciprocal function ever touch 0? No. So there are none. It doesn't have a 0. Now some of these will, some of these won't. Yeah, it depends. I am going to do now the y-intercept. The y-intercept is the easy one. You just plug in 0, what you get is what you get. That's 1 over negative 8, or negative 1/8. So we do hit the y-axis at negative 1/8 because we have scooched to the right. That bottom piece scooches to the right, and it does cross over the y-axis a little bit. Okay, and that could happen when we scooch it a little bit left or right. Now let's talk about our vertical asymptotes before we do domain. I always do holes in vertical asymptotes before domain because they're linked together. A vertical asymptote is where the bottom equals 0. If it is in reduced form, it is in reduced form. It's at 8. Remember, this function's vertical asymptote was at 0. It scooched to the right 8 units. Doesn't it make sense that it's over there at 8? So our domain has to skip over 8. Now, since we know what the graph is doing so very clearly, feel free to graph it first and then answer these questions. That's okay. And then the last thing that we need is the horizontal asymptote. See how it says to explain what happens at the asymptotes? We'll do that on the graph paper. Okay, we'll do that on the graph paper. And so the horizontal asymptote, remember, because we have our x's only in our denominator, it always goes to 0. That's what our parent function did. This function did not move up or down, so it just kind of scooched over to the right. Okay, so we're going to graph A, and I'm going to kind of split this graph paper into two pieces. So let's make one of our graphs kind of far over here, because I need to go all the way to 8 to the right. I can't seem to get it on the line there. Every time I do it, it snaps in place in the wrong spot. Yeah, that's pretty good. Okay, so just when I graphed our original function, when I graph this, I always put on my asymptotes first. So over at positive 8, I need an asymptote. Okay. So now I've got my graph paper. Let's plug in a few points. We already know that at 0, we were at -1/8. I mean, you know, guesstimate, I don't know. I can't get that close, but I'll try. I usually, when I'm graphing a rational function, if my vertical asymptote is 8, I will plug in 1 below it and 1 above it. Oh, I'm sorry. If I could do that. 1 below it and 1 above it. So 7 and 9 are going to be nice values. If you plug in 7, you get 1 over -1, you get -1. If you plug in 9, you get 1 over 1 or 1. Now, think about the parent function. We always graphed 1, 1, and -1, -1. It doesn't make sense that we would get those values. So put a little dot here and a little dot here. So here we're going to follow the asymptote. Here we're going to follow the asymptote. Here we're going to follow. And I didn't really put on the horizontal line. Let's add a little. I'm never very good at drawing these, but okay. So we've got those two pieces. Now I want you to put this notation on the graph. Okay, first let's do the correct notation for our vertical asymptote. So our vertical asymptote is at 8. As we approach 8 from the right, our y is going up to infinity. As we approach 8 from the right side, our y is going up to infinity. As we approach 8 from the left side, our y is going down to -infinity. This side's going up, this side's going down. That's what that notation means. Now let's talk about our end behavior. What are our far ends doing? As x goes to positive infinity, that just means right, our y heads to a height of 0. As x goes to -infinity, our y goes to a height of 0. So when it says to describe what is happening at your horizontal and vertical asymptotes, that describes our vertical asymptote. This describes our horizontal asymptote. And we can also say that our horizontal asymptote is y equals 0. So that's everything we could possibly need to know about that graph. Move the asymptotes first and then plug in a few points, and that will give you what's happening. Okay? Move the asymptotes first and then plug in a few points, and that will tell you what's happening. Okay, now let's move on to B. What happens because there is a squared there? I will tell you that the zeros are still none. The y-intercept gets a little closer to the y-axis because when we plug in 0, now it's 1 over negative 8 squared, or 1 over 64. Very small number. We're even closer to 0 quicker. And you'll notice instead of being at the negative 1/8, it's at a positive 1 over 64. The vertical asymptote still occurs when x minus 8 equals 0, or at 8. We still have that vertical shift to the right 8 units. So our domain is exactly the same. The x's in our denominator are more. Our horizontal asymptote is the same. So what's the difference? The difference is when we square a negative, it always becomes a positive, right? So the only difference in this graph versus this graph is the fact that this piece will no longer live in that location. It's going to flip because when I square a negative, it becomes a positive. That is the only difference. I mean, it's kind of stretched a little, but that's the main thing. So let's now put all this information onto our graph. Okay. So I am going to kind of scooch it down here so there's a slight difference. Hello there. Oh, thank you. Thank you so much. So now, when you graph these, the first thing that you do is you put on your asymptotes. So let's put on a vertical asymptote at 8. Last time it took me a while, but let's put our horizontal asymptote at 0. So let's put x equals 8, y equals 0. Now, hopefully you're just going to start to know where the points happen. But if we plug in 7 and 9 again, 1 on each side of our asymptote, if we plug in 7, we get positive 1 because we get 1 over negative 1 squared. If we plug in 9, we get positive 1. So now we have 2 pieces up there. Remember, we got a y-intercept of 1 over 64. I can't even get that close, but yeah, we got 1 over 64. So now we have a piece here and a matching mirrored piece over here. This is what's called an even function. Well, it has symmetry around the vertical asymptote x equals 8. So I guess it's not quite even, but okay. Anyway, let's put that same notation we put. Let's describe what's happening at our ends and at our vertical asymptote. Let's start with the vertical asymptote. As x approaches 8 from the right side, our y is going up to positive infinity. As x approaches 8 from the left side, our y is going up to positive infinity. Both ends head upward. Now, this becomes important if you ever take calculus in your future, because if you take calculus in your future, that is called a limit. And the limit as we approach 8 on our first function doesn't exist, if you're a Mean Girls fan. And the limit as we approach 8 on our last function does exist. It goes to infinity. Okay. Now let's talk about our limits on our ends. As x approaches infinity, our y is heading to 0. as x approaches negative infinity, our y is heading to 0. Both of these functions head to 0 on the ends. Okay, so it's important that you know that notation. They will use that notation in IMath, I believe. Okay. Now, I do not believe we're going to have enough time to do all of these today. We're going to do as much as we can. Whatever we finish, we finish. Otherwise, I don't care. Okay. I would like to do one that has a hole. So let's focus on 1 and 4. Okay, we're going to do those. I don't think we're going to do 2 and 3. I don't think we're going to have time, but that's okay. Okay. So yesterday when we did 6.1, I had a little list that I did. I got it into factored form. I found the holes, I found the vertical asymptote, I found the domain. We're going to do that exact same thing here, but for the first time, we're going to put it on the graph paper. We're going to put it on the graph. We're going to see how that shows up on a graph. So do you see how I put the order here, but I'm going to do, well, you'll see. First, get into factor form. It's factored. X minus 3x plus 2, you can't factor that. Next thing you should always do, I'm not going to go in necessarily the order shown there. The next thing I'm always going to do is I am going to find any holes. There isn't a factor on top that matches factor on bottom. There are no holes for this particular function. Next thing I'm going to do is the vertical asymptotes. Any remaining factors once reduced, where does our denominator equal 0? So in this case, the reduced form is x plus 2. It equals 0 at negative 2. So our domain comes next. Take out any holes or vertical asymptotes. The only one is at negative 2. Then I do the zeros in the y-intercept. Zeros is where the top equals 0, because a fraction only equals 0 when its top is equal to 0. So at 3. The y-intercept, you just plug in 0 and hope for the best. You get negative 3 over 2. The only thing we have not done on this list is our horizontal asymptotes. So we'll call that F. So again, for these, let's always kind of do it in this order. It's very helpful. So what are the ends doing? Our first example that we graphed together, the only x's we had were in our denominator. The higher power is in our denominator, which goes to 0. Here, the horizontal asymptote, because the top power's lead term is an x and so is the bottom, when they match, we just get to think about those lead terms. If you reduced them, what would you get? So you get to use the coefficients. So it's just 1 over 1 or 1. We're not going to do that. So now let's put the pieces together. First thing we should always put on our graph paper are our vertical and horizontal asymptotes. There is a vertical asymptote at negative 2. There is a horizontal asymptote at 1. Now we need points on our graph paper. We need points on our graph paper. The only points we know so far is at 3, we're at a 0. And we hit our y-axis at negative 1.5. So we can clearly see sometimes this happens that we have to follow the asymptote, go through these points, follow the asymptote. So that piece is pretty darn well defined. And again, this is a function. Plug in as many points as you want to get the swoop of the curve, but they have to follow your asymptotes. So the only thing we don't know is what's happening to the left of -2. So I'm going to plug in now. Definitely let's plug in -3 and see if that gives us enough information. If you plug in -3, you get -6 over -1 or 6. That tells me my swoop is captured in that little corner. Because I got to go up here and down there. I am always following the asymptotes on a rational function. Now let's put in our notation. Let's put in the correct notation and let's see what happens. Okay. As x goes to infinity, y is heading to 1. That's our horizontal asymptote. We have a horizontal asymptote at 1. As x goes to -infinity, y is heading to 1. Remember, we had a vertical asymptote at -2. Look what's happening here. As x approaches 2 from the left, our y is going to infinity. Here, as x approaches 2 from the right, y is going to -infinity. So sometimes from the right, we go down and not up. So that's what our graph looks like for everybody good with that one? Okay. So let's do one more, and then we'll turn this in. So let's do problem number 4. Now, hopefully I remember my list. So the first thing we're going to do is get it into factored form. So k of x is x minus 2 over x plus 2 and x minus 2. Because that can tell us if there are any holes. Now remember, a hole appears when there is a factor in the top and the factor in the bottom. Just set that equal to 0 and solve for x. X minus 2 equals 0 at 2. And then take it out and remove it. For the rest of the problem, we can use the simplified version. That is one of our family of parent functions. Move to the left 2. So keep that in mind. We know what one over x plus 2 looks like. It's our reciprocal function moved to the left 2. But let's do everything else. The next thing I would always do are the vertical asymptotes. That's where our bottom remaining factor equals 0 or at -2. That leads us now to do domain. What values do we skip? We have a hole at +2 and a vertical asymptote at -2. Skip both of those, and that's your domain. -infinity to -2, skip it. -2 to 2, skip it. 2 to infinity. So you'll notice that we have to skip our infinite discontinuity, our vertical asymptote at -2, And our removable discontinuity, our whole at positive 2. Think about our little math bug. If he was walking along the graph, he'd be on this nice little smooth curve, and then he'd come across a vertical asymptote. He would have to leap across there to get to the next piece. There's a hole. If he falls in the hole, he's going to die. He doesn't want to do that. He leaps across there to our next piece. Okay, so if you think about it, our domain should include the places our little math bug could walk, and should not include the places where he comes across a barrier or some kind of issue. Okay. Okay. See, you'll remember that now, won't you? Okay, next, let's talk about the zeros. Did I call it E and F, I think? Yeah. E were the zeros and the y-intercept. So the zero of a function is, where is the top equal to 0 in the simplified form? Is 1 ever going to equal 0? Nope. So there are none. So this graph never touches our y-axis. The y-intercept, plug in 0 into our reduced form. We get 1 over 2. Which leads us to our horizontal asymptote. The higher power is in the bottom, whether you look at the reduced form or the original. So our horizontal asymptote is at 0, which makes sense because we never touched the y-axis. I'm sorry, the x-axis. So there you go. So now we're ready to graph it. So let's make our graph paper all beautiful. Well, you know, as beautiful as I ever do. I don't know. Anyway. First thing we're going to put on there are both our vertical asymptotes and our horizontal asymptotes. So over at -2, we have a vertical asymptote. At 0, we have a horizontal asymptote. Now, for the very first time, we have come across a graph with a hole in it. So we are definitely going to need to know what happens at the hole of 2. We're going to use the simplified version to help us graph it and find out what the hole is, where the hole is at. If you plug in 2 to the simplified version, we get 1/4. But we need some points here. Let's plug in -1. That's to the right of our vertical asymptote. If you plug in -1, you get 1. Let's plug in -3. You get -1. Let's put those points on. But at 2, we are going to physically draw a little open circle, a hole. Okay. So over here at 2, at 1/4, put a physical little open dot. Remember, that's the little hole the math bug is not allowed to fall through. So you're warning him. Okay. At -1, we were at 1. At -3, we were at -1. This piece follows the asymptotes. This piece follows the asymptotes. And then let's put on our correct notation around the vertical and horizontal asymptotes, the end behavior and the infinite discontinuity. Let's put those on there so that all is right with the world. Okay. So let me kind of zoom into my graph slightly. Let's do the ones around our vertical asymptote. As we approach x value of -2 from the right side is going up to positive infinity. Let's approach -2 from the left side. As we approach -2 from the left, our y is going down to -infinity. So that's the notation that goes with our vertical asymptote. Now let's use the correct notation with our end behavior, our horizontal asymptotes. As x goes to infinity, positive infinity. So as x is going to the right, our y is heading to that horizontal asymptote value of 0. As x goes to the left, our y is also heading to a height of 0. So you should have every single piece and part you need to start graphing these. As you do the 6.1 and 6.2 homework in Desmos, please use Desmos as your guide if you're stuck. On Monday, we will do 6.3. Any pre-classes that are showing up in iMath at this time are going to magically disappear, so just ignore them. But the homeworks are still there. So you have 2 homeworks due on Sunday, 6.1 and 6.2. Over Thanksgiving break, you're going to have a 6.3 homework and video to work on. So there you go.